I'm Bill Langdon, and what I want to talk to you about is our paper, Measuring Failed Disruption Propagation in Genetic Programming. So the idea is we're going to use information theory to show why entropy loss means that deep mutations don't change fitness. So that's what the graph is trying to show. As we move away from some sort of disruption within our GP tree, the chance of actual disruption in terms of fitness changes falls away. So what I'll try and do is give a brief introduction what we mean by fitness failed disruption propagation. The paper itself has got a lot about information theory. The first part is looking at Monte Carlo tests where we actually do a huge number of simulations. And it also contains some results which show that at best, in a black box scenario, the effectiveness of a test suite grows only slowly, effectively and logarithmically with the increase in number of test cases. But what I'm going to talk today about is essentially the idea of the last part of the paper, where we take some highly evolved GP trees and artificially insert errors within them, and then trace the impact of those errors and essentially verify the results that we get from the Monte Carlo simulations. So the idea with failed disruption propagation comes from software engineering. So we have in a little example here of a small piece of erroneous code. So the idea is this function is supposed to, instead of dividing by 10 and taking the truncating downwards, it's supposed to round. But the second line where we assign the variable a to a value, we actually assigning it the wrong value. So we've got an error in our code there. But the following line, the line with B, is a line that actually loses a fair amount of entropy. So if we test our code on inputs of 0, 1, and 10, it actually calculates the right answer. So despite the error, we still have the correct answer. And so essentially we're viewing this as we're executing a destructive operation, an erroneous operation. So our line where we assign A is in error, we execute that, we do create an error, but the error fails to propagate because it has to pass through the line B, which is an entropy loss region. So we fail to propagate the error, and the return statement in those test cases actually returns the right answer. So I'm going to, again, from the point of view of time-wise, I'm going to skip past those. Essentially, the idea here is we have we want to treat our functions as though they were information files. So our function here takes two 32-bit values and generates a 32-bit output. From an information theory point of view, it takes two 32-bit quantities, each of which can contain at most 32 bits of information. So we have at most 64 bits of information coming into our funnel, but we have at most 32 bits going out. So the funnel is capable of losing information, and we can cascade these. So if we have nested functions, so here we have 5 nested functions, and at each point we may lose information. So the red arrow is supposed to indicate some form of disruption which enters our hierarchy and is progressively diluted. So At each stage, we may lose information about the error, and by the time we reach the output, that error may be entirely invisible. It's failed to propagate to the output. So as I said, I'm going to skip past the Monte Carlo simulations and effectively move on past the argument about log n test effectiveness. And essentially, the idea is, in the second part of the experiments, we evolve our GP, we allow it to run past the point where it finds solutions, so that we're getting large GP trees, and in particular, we get deep GP trees. And then from each of those trees, what we do is artificially insert an error. So at every point within the program, every node in the tree, we artificially perturb the evaluation. In the first experiment, by simply adding 1 to whatever evaluation it had before. And then we follow the perturbation up through the tree towards root node. And in particular, we're interested in the case where failed disruption propagation means the disrupted and the original evaluations are identical. And what we see is there's some sort of warm-up period close to the disruption where the disruption propagates fairly effectively. And that's followed by a long tail where, as we move further away from the disruption point, the chance of the disruption propagating falls in an exponential way, as predicted by the Monte Carlo simulations. So again, skipping past for just, just from the table, just to emphasize, although we get a lot of variation between runs, on average, here we're seeing more than 80% of the perturbations do not reach the root node, and therefore do not have any impact on the fitness of the tree. This is a bit of a complicated example, but what we're looking at here is the variation in failed disruption propagation by test value. So what I'll show you is slightly easier to read graph. Here we're looking at the same sort of data, but we're looking at 10 different runs. So each of the colors indicates a different run. And you can see there is considerable variation between the runs, but they show the same general trend, that there's a rapid initial rise and then followed by a long, approximately exponential tail. And the straight lines there are RMS best fit to put a straight line through the scope. So remember, this is a log plot, so a straight line corresponds to exponential decay. And as I said, there's variation between the runs, but on this particular test case, which is test case near 0, we see the disruption falling as about the distance divided by 5. This graph is essentially, so the test value is 0 from here corresponds to the middle of this graph. So the slope of the graphs is plotted here, and so you can see that test values 0 for all 10 of our runs works out as being the least able to do penetrating up the GP tree. In other words, it's the least effective test case, whereas test cases near plus or minus 1 are considerably more effective at picking up the runtime disruption. And again, from the point of view of time, I'm going to skip past that. So essentially, I've not really talked about it, but the Monte Carlo simulations aim to test to sample the whole of the search space, and they show that the affective fitness disruption falls inversely in proportion to the size of large trees. There's an argument in the paper which shows that the effectiveness of test suites only grows slowly with the increase in the number of test cases. This is all assuming that the tests are independent of each other, and effectively that's the best we can hope for in black box testing. In terms of the GP experiments, when we both disrupt by adding one to the evaluation, or if we just totally randomize the evaluation, we get similar behavior. In this case, we're seeing, on average, more than 80% of the time, failed disruption propagation means that the error we've inserted has no impact by the time it reaches the root node. In terms of information theory, what it predicts is we're bound to lose information. And so deeply nested expressions must suffer from failed disruption propagation. Or even if the entropy loss is larger than we see here, the expressions need not be actually all that big to see a significant effect. And so what we argue for is, if we want to have continued rapid evolution, so to allow large programs to evolve, the code must remain shallow, or there must be side effects that convey the disruption to the environment. Conversely, changes in the environment must be intimately connected with the evolving code.